Hi, let us discuss about matrices. A matrix is a rectangular array or table of numbers or symbols or expressions arranged in rows and columns. And the dimension of a matrix is represented by m by n if there is m rows and n columns. Now first consider transpose of a matrix. Transpose of a matrix. The transpose of a matrix of order m by n is a matrix n by m obtained by interchanging the rows and columns. So if I interchange the rows and column of a matrix, then I will get the transpose of that matrix. Suppose our original matrix A is equal to A11, A12, A21, A22, then A transpose will be equal to A transpose is equal to A11, A21, A12, A22. So this will be the transpose of this matrix. Now, what are the properties of transpose? The first property is A transpose whole transpose is equal to A. Second property, if you have lambda, a scalar quantity, a number times A transpose, then this will be equal to lambda into A transpose. Then A plus B whole transpose will be equal to A transpose plus B transpose. And the fourth property, A into B whole transpose is equivalent to B transpose A transpose. So this property we remember ചെയ്യണം. A into B whole transpose is equal to B transpose into A transpose. Now next point is the complex conjugate of a matrix. Complex conjugate of a matrix. The matrix obtained by replacing all elements by the corresponding complex conjugate is said to be complex conjugate of a matrix, and it is denoted by A star. So if matrix AI is represented by Aij, and if its order is m by n, then matrix A star, that is complex conjugate of that matrix, will be Aij complex conjugate m by n. Now, as similar to the transpose, now here also we have certain properties. The first property, A complex conjugate whole complex conjugate is equal to A. Second is, if you have a number lambda, then a matrix A, then lambda A whole complex conjugate will be equal to lambda complex conjugate into A complex conjugate. Then A plus B whole complex conjugate is equivalent to A complex conjugate plus B complex conjugate. Then A into B complex conjugate. A into B complex conjugate will be equal to A complex conjugate into B complex conjugate. Okay. Now next point is Hermitian conjugate of a matrix. Hermitian conjugate of a matrix. Now the Hermitian conjugate of a matrix is also known as adjoint of a matrix. Adjoint of a matrix. The Hermitian conjugate of a matrix is the transpose of the complex conjugate, or equivalently, this is the complex conjugate of the complex conjugate of its transpose. Or Hermitian conjugate is, we symbolically represent Hermitian conjugate by a dagger. So a dagger will be transpose of the complex conjugate, that is A star whole transpose, or A transpose in the conjugate kandalu madi, or it is equivalently the complex conjugate of its transpose. So A transpose whole complex conjugate. So that is the Hermitian conjugate. Now similar to these four properties, again here we have four properties, that is A dagger whole dagger will be equivalent to A. Second property, lambda times A whole dagger will be equal to lambda star into A dagger. This is not transpose, this is dagger. Then A plus B whole dagger will be equivalent to A dagger plus B dagger. Then A into B whole dagger will be equivalent to B dagger A dagger. So these are the properties. Now let us consider some special square matrices. The first one is symmetric matrix. So the first category is symmetric matrix. A matrix is said to be symmetric if A transpose is equivalent to A. If A transpose is equivalent to A. That is, if transpose of a square matrix is equal to the matrix itself, we say that it is a symmetric matrix. That means here Aij will be equal to Aji for every I comma j. Now next is anti-symmetric matrix. Anti-symmetric matrix. Here A transpose will be equal to minus A, or you can say Aij is equal to minus Aji for every I comma j. Now if I is equal to j, that is means diagonal element. If I is equal to j, then you will have Aii is equal to 0. That is, all diagonal elements are 0 for anti-symmetric matrix. Now third category is orthogonal matrix. Orthogonal matrix. A matrix is said to be orthogonal if A transpose is equivalent to A inverse. A transpose will be equal to A inverse. Or we can say A transpose into A is equal to A into A transpose is equal to identity. Okay. Or just in the Aij notation, you will have summation I Aij Aik is equivalent to delta Jk. Now next category of matrix is Hermitian matrix. Fourth one, Hermitian matrix. A matrix is said to be Hermitian if A dagger is equal to A. Also we can define anti-Hermitian matrix or skew-Hermitian matrix. Skew-Hermitian. Now anti-Hermitian or skew-Hermitian means A dagger is equal to minus A. So a Hermitian matrix is the complex analog of the real symmetric matrix. Hermitian matrix is the complex analog of real symmetric matrix. In a Hermitian matrix, you can write down the relation as Aij is equal to Aji star for every I comma j. For every I comma j, in a Hermitian matrix, Aij is equal to Aji star. Now if you consider the diagonal elements of a Hermitian matrix, then diagonal elements of the Hermitian matrix will be real. Diagonal elements will be equal to real numbers, because then only this relation can be satisfied. Aij is equal to Aji star. Because for diagonal elements, I is equal to j and you will have Aii. And this relation satisfies Aii should be equal to Aii complex conjugate. ഇതെപ്പോഴാണ് for every I ഇതെപ്പോഴാണ് സാറ്റിസ്ഫൈ ചെയ്യുക? ഈ സാറ്റിസ്ഫൈ ചെയ്യണമെങ്കിൽ ai ഒരു റിയൽ നമ്പർ ആവണം. That's why diagonal element should be real numbers. Now if you consider skew Hermitian matrix, for skew Hermitian matrix or anti-Hermitian matrix, a dagger is equal to minus a. So aij should be equal to minus aji star for every I comma j. Now if I is equal to j, then you will have aii is equal to minus aii star, or aii plus aii star is equivalent to 0. Now when this condition will be satisfied? So let us take aii is equal to x plus iy. Then aii star will be equal to, that is complex conjugate of this element will be x minus iy. Now our condition is aii plus aii star is equal to 0. So that means x plus iy plus x minus iy is equal to 0, or 2x is equal to 0. So x is equal to 0. Now when x is equal to 0, our number aii is a purely imaginary number. Now this condition can be satisfied if aii is equal to 0 also. If aii is equal to 0, then aii complex conjugate 0 ആവും. Then a 0 plus 0 0 കിട്ടും. So that means for a skew symmetric matrix, the diagonal element can be 0 or it can be pure imaginary number. It can be pure imaginary number. Now next matrix is unitary matrix. Unitary matrix. A matrix is unitary if a dagger is equal to a inverse, or we can say a dagger into a is equal to a into a dagger is equal to identity. Now if you consider the determinant of a dagger into a, then this will be equal to determinant of identity, because a dagger into a is equal to identity. Now this part can be written as the determinant of a dagger into determinant of a, then this will be equal to determinant of a star into a, and that will be equal to determinant of a square, and that is our determinant RHS identity ആണ്. So this implies that the determinant of a is equal to plus or minus 1, because determinant of identity is 1. So that means for a unitary matrix, the unitary matrix is non-singular, and the determinant of a unitary matrix is always unit modulus. So our result is unitary matrix is non-singular. Unitary matrix is non-singular. Second, determinant of a unitary matrix is always unit modulus. Determinant of unitary matrix is unit modulus, is of unit modulus. Okay. Now let us prove that every square matrix can be uniquely expressed as sum of a symmetric and a skew-symmetric matrix. So let us consider, let A be a square matrix and A transpose be its transpose matrix. Then a matrix A can be written as A is equal to half A plus A transpose plus half into A minus A transpose. ഇവിടെ മൈനസ് എ ട്രാൻസ്പോസും പ്ലസ് എ ട്രാൻസ്പോസും ക്യാൻസൽ ചെയ്യാം. ദെൻ ബാക്കി ഉണ്ടാവുക ഹാഫ് എ പ്ലസ് ഹാഫ് എ വരും. ഓക്കെ, നൗ ലെറ്റ് us take this part as P and this is equivalent to Q. So A can be written as P plus Q. Now let us consider P transpose. Then what is P transpose? P transpose will be equal to half into A plus A transpose. Now half ഒരു number ആണ്, so ഈ halfന് transpose consider ചെയ്യേണ്ട ആവശ്യമില്ല. So this will be equal to half into A transpose plus A transpose whole transpose. And A transpose whole transpose is A. So this is equal to half into A transpose plus A, and that is equivalent to P. Because A transpose plus A നമുക്ക് ഇത് commutative ആയതുകൊണ്ട് A plus A transpose എന്ന് എഴുതാൻ പറ്റും, and that is equivalent to A, P. So our result is P transpose is equal to P. That means this part, P എന്നുള്ള ഈ part, this part symmetric ആണ്. So this shows that P is symmetric. Okay. Now let us consider the second part, Q, and take the transpose. So Q is half A minus A transpose. So Q transpose will be equal to half into A minus A transpose whole transpose, and this will be equal to half into A transpose minus A. Again ഇവിടെ A transpose whole transpose വരും, അത് A വരും. Okay. So this is equivalent to minus half into A minus A transpose, and A minus A transpose is equal to Q. So this is equivalent to minus Q, and our result is Q transpose is equivalent to, not Q dagger, Q transpose. Q transpose is equivalent to minus Q. So this implies that the part Q is anti-symmetric or Q symmetry. So this shows that our representation half A plus A transpose is symmetric, and this part is anti-symmetric. So thus a matrix can be expressed as a sum of symmetric and Q-symmetric representation. Now in our statement we are required to show that the every square matrix can be uniquely expressed as a sum of symmetric and Q-symmetric matrix. So we have to prove that this representation, that is A is equal to half A plus A transpose plus half A minus A transpose, this representation is unique. So next I am going to prove that representation is unique. That is, there is no possible other representation. So let us consider A is equal to R plus S as some other possible representation, and R transpose is equal to R, and S transpose is equal to minus S. So R transpose, this part symmetric part of this part anti-symmetric part. Okay. Now our representation is A is equal to R plus S. So A transpose will be equal to R plus S transpose. That will be equal to R transpose plus S transpose. Now R transpose is equal to R. S transpose is equal to minus S. So this will be equal to R minus S. So if A is equal to R plus S, then A transpose is equal to R minus S. So if I find out A plus A transpose, then this will be equal to R plus S plus R minus S. So that is 2R. Now if I find out A minus A transpose, then this is equivalent to R plus S minus R minus S. So that is equal to 2S. Okay. So this implies R is equal to half into A plus A transpose. And from here we get S is equal to half into A minus A transpose. So this proves that our representation, now what is R? R is equal to half into A plus A transpose. S is half into A minus A transpose. This shows that our representation A is equal to half into A plus A transpose plus half into A minus A transpose is unique. If A and B are symmetric matrix, then we have to show that A into B is symmetric if and only if A and B commute. Now if A is symmetric, then that means A transpose is equal to A, and if B is symmetric, then that means B transpose is equal to B. And AB is symmetric if A into B whole transpose is equivalent to AB. Okay, now let us consider AB whole transpose. AB whole transpose. Now from the property of transpose, this will be equal to B transpose into A transpose. And this is equivalent to B transpose is B, A transpose is A. So this is equivalent to B into A. Okay. AB whole transpose is equal to AB. Now we got AB whole transpose is equal to BA. AB whole transpose is equal to B into A, equation 2. Now these from equation 1 and 2, AB whole transpose, from these two equations, AB is equal to BA. That means AB minus BA is equivalent to 0, or A and B commute. A, B commutator is equal to 0. So AB symmetric anengil AB യും symmetric ആവും if A commutator with B is equal to 0. Now here we have to prove that the product of two orthogonal matrix is also orthogonal. So let us consider two orthogonal matrix A and B. Now if A is orthogonal, then A transpose will be equal to identity. And if B is orthogonal, then B transpose will be equal to identity. Then we have to prove that the product AB is also orthogonal. So let us consider the product AB, and AB is orthogonal if A into B into A into B whole transpose is equal to identity. This prove ചെയ്തു കഴിഞ്ഞാൽ product AB യും orthogonal ആണ്. Okay, so let us consider A into B into A into B whole transpose. So if you consider this term, then this is equivalent to AB into, ഇവിടെ നമ്മൾ transpose in the property use here. So this will be B transpose into A transpose. Now B into B transpose is identity. So this is A into identity into A transpose. Now A into identity is equal to A. So this is A into A transpose. And what is A into A transpose? A into A transpose is identity. So we proved our relation, that is A into B into A into B whole transpose equal to identity. This shows that the product AB is orthogonal, or the product of two orthogonal matrix is also orthogonal. Now let us consider, prove that the rotational matrix cos theta minus sin theta cos theta is orthogonal. So let us consider this matrix A is equal to cos theta minus sin theta cos theta. Let us consider A transpose. A transpose will be equivalent to cos theta then sin theta minus sin theta. Now let us consider the product A into A transpose. This will be equal to cos theta minus sin theta cos theta into A transpose is cos theta sin theta minus sin theta cos theta. So this will be equivalent to cos theta into cos theta, that is cos square theta plus sin theta, cos square theta plus sin square theta, then cos theta into sin theta minus sin theta cos theta. So cos theta sin theta minus sin theta cos theta. Again here you will have cos theta sin theta minus sin theta cos theta, that will be 0. And here you will have cos square theta plus sin square theta. Cos square theta plus sin square theta. So this will be equal to 1 0 0 1. That is A transpose is equal to identity. So now next property is, an n cross n matrix A is orthogonal if and only if its columns x1 x2 up to xn form an orthonormal set. Let us consider again our orthogonal matrix cos theta minus sin theta, cos theta. Now form its column vectors. So the first column vector is cos theta sin theta and name it as x1. Next നമുക്ക് ആകെ രണ്ട് കോളം ഉണ്ട്. x2 will be equal to minus sin theta cos theta. Then the theorem says that these columns form an orthonormal set. So that means നമ്മൾ x1 transpose into x2 consider ചെയ്ത് കഴിഞ്ഞാൽ you will get 0. This will be equal to 0. Then x1 transpose x1 will give you identity 1. x2 transpose x1 will give you 0 and x2 transpose x2 will be equal to identity. ഇങ്ങനെ ഫോം ചെയ്താൽ x1 x2 these columns will form a orthonormal set. Okay, so നമുക്ക് ചെയ്തു നോക്കാം. Now what is x1 transpose x2? x1 transpose x2 will be equal to x1 എന്ന cos theta sin theta. x1 നെ ട്രാൻസ്പോസ് ചെയ്യണം. So x1 ട്രാൻസ്പോസ് ചെയ്യുമ്പോൾ cos theta sin theta എന്ന് പറയുന്ന ഒരു റോ വെക്ടർ വരും. Now this x1 is a column vector. ഒറ്റ കോളം മാത്രമേ ഉള്ളൂ. No number of rows ഉണ്ട്. So x1. Now x1 ട്രാൻസ്പോസ് എടുത്താലോ? x1 ട്രാൻസ്പോസ് എടുത്താൽ നമുക്ക് റോ വെക്ടർ കിട്ടും. ഒരു റോയും more than one column ഉള്ളതാണ് റോ വെക്ടർ. cos theta sin theta. This is x1 transpose. Now what is x2 transpose? x2 transpose will be equal to minus sin theta cos theta. Again this is a row vector. x2 transpose a row vector ആണ്. x1 transpose a row vector ആണ്. x1 is said to be a column vector. x2 is another column vector. Okay. Now x1 transpose x2 will be equal to cos theta into sin theta. Then x2 is minus sin theta cos theta. Minus sin theta cos theta. So this will be equal to cos theta into minus sin theta plus sin theta into cos theta. That will be equal to 0. So നമ്മൾ ഇത് prove ചെയ്തു. Let us consider the next term x1 transpose into x1. So this will be equal to cos theta sin theta. Then again cos theta sin theta. Okay. This will be equal to cos square theta plus sin square theta. That is equal to 1. Similarly, we can prove that x2 transpose into x1 is 0 and x2 transpose into x2 is equal to 0. Now a note, the set of eigenvectors corresponding to distinct eigenvalues are orthogonal, but the different eigenvectors corresponding to repeated eigenvalues may not be orthogonal. Now using Gram-Schmidt orthogonalization procedure, this can be made orthogonal.